I'm enthusiastic about hearing about the EU MRV and their goal to include non-CO2 effects, because I think there might be critics in saying that it's a bit too early, but we're first monitoring and then legislation comes later, right? So it's a good motivation for further research to be done. And my research is mostly on the observational side of looking at contrails. And I think within a system like the EU MRV, models of contrails and other aviation non-CO2 effects are always going to play a central role, right? But what my research really tries to do is to gather the observations to test those models and see how accurate they are.
Welcome to the Aerospace Ambition podcast. In this episode, we'll explore contrail management. I'm Marius, an aerospace engineer and your host. Today we have the pleasure of hosting Dr. Vincent Meijer. Vincent recently completed his PhD at MIT's Laboratory for Aviation and the Environment under Professor Steven Barrett. His research focused on remote sensing of contrails and improving contrail forecasting. Vincent is now an assistant professor at Delft University of Technology in the Aircraft Noise and Climate Effect Group within the Aerospace Engineering faculty. He's also involved in EU projects like BeCoM, which stands for Better Contrail Mitigation. Vincent, welcome to the show.
Yes, thank you, Marius, for that welcome. I'm super excited to be here.
I'm excited too, and thanks for being here. And I'd like to start with a little bit of a personal question. And don't worry, this podcast will not become a lifestyle podcast at all, but starting it off here, since I mentioned it in the intro and you worked with Steven, and Steven has been a guest on episode 9. So What is it like working with Steven?
Well, first of all, it's really good. He has given me the opportunity to do the research that is now essentially part of my job, right? And he basically exposed me to this very interesting research area of contrail science and also contrail management. And I think we've had a very fruitful, slightly more than 4 years working together. And I'm still very much in touch with him now that he's at his new position at Cambridge. And I can only say good things about Steven, to be honest. And he is someone who is always trying to push the state of the art further. And he's overall really a good person to work with. Also at a personal level, he's very nice to interact with and have some occasional dark British humor to go with it, which I also can really appreciate.
Yeah, that's also something that I experienced during the interview, and I'm sure he's happy to hear about that from you. So I wanted to start off by asking you a question about your research focus that is, going beyond the introduction, but I thought to spice it up a little bit and make it a little bit more concrete, especially in the day and age that we are living in and the challenges that we are facing right now. And as you know, in order for things to really get managed or to get implemented, we need legislation. And right now, the topic of the day is the MRV scheme. And of course, its scope with regards to non-CO2 effects is being discussed right now. So I'm going to rephrase the question about your research and put it in that context. So how does your work relate to that? And where does it actually help us to achieve progress for that?
Let's say I'm enthusiastic about hearing about the EU MRV and their goal to include non-CO2 effects, because I think there might be critics in saying that it's a bit too early, but we're first monitoring and then legislation comes later, right? So it's a good motivation for further research to be done. And my research is mostly on the observational side of looking at contrails. And I think within a system like the EU MRV, models of contrails and other aviation non-CO2 effects are always going to play a central role, right? But what my research really tries to do is to gather the observations to test those models and see how accurate they are. And what I'd ultimately like to be able to do is to assess different models for these impacts and then come up with essentially error estimates. So how accurate are these models? For example, you could say we take model A, and then from model A we know that if it says this is the radiator forcing, in reality it's going to be that radiator forcing plus minus a certain amount. And then what I'd like to see is for the EU MRV system to basically include that plus minus, right? Really incorporate the uncertainty, because we're never going to be perfectly certain. But in my opinion, it's always better to be very aware of how wrong you are and then take that into account in this accounting system. And how we're going to do that, I'm really not sure. But that is one of my foremost goals in my research. Taking these models and then figuring out how good are they by comparing them to observations and using that information in a productive manner.
Right. And you've mentioned the term error estimates.
Mm-hmm.
When you speak with people in the industry or in the ecosystem, they usually use the term uncertainties. Is that a synonym, or how do these terms distinguish?
Let me put it like this. An error is usually uncertain, because if you were certain about the error, you wouldn't make the error, right? So, for example, if you think about typical uncertainty distributions like a Gaussian, then what we're certain about is sort of the spread, but we're not really certain about which side of the estimate is the error going to, right? Because if we knew that, we'd be able to correct for it, and then you have a different kind of uncertainty. So they're very closely related. I think uncertainty sometimes is used a bit as a catch-all term for many different things. I mean, in principle, there's just a lot of things that we don't know. So uncertainty obviously is a word that is used frequently. But when I talk about error estimates, yeah, you can express this as an uncertainty from the model, essentially.
And one of the parts of the data pipeline or the prediction pipeline is the contrail detection. And you've mentioned that you are trying the research to progress also in the area of observations and using actual observations and not just rely on models.
Mm-hmm.
So how effective are our current methods for detecting contrails and also matching them then to specific flights?
There's a couple of different ways to express that, right? Ultimately, we'd like to compare things to what we call a ground truth, which is basically saying, okay, this is the best possible estimate of a certain quantity, and then we're going to compare whatever our models say to that ground truth and score them, essentially, come with an error estimate, essentially. So I think when you compare our abilities to detect contrails in satellite images, right? And most of the focus recently has been on geostationary satellite images, so that we can actually observe contrails every 5-10 minutes, essentially. And if you compare to the human labels, right? Because typically these detection methods require manually labeled contrails to be trained, essentially, then we're getting progressively better and better. But the question also are the human labels really the ground truth, right? So in that sense, there's this other sort of part of the pipeline that might introduce errors, which is going from the ground truth to the human labels. And I think that we're just starting to really look at what that does, right? Because you might have a detection model when you compare it to the human labels, it scores very well. But then if the human labels are not actually reflecting the ground truth, then you're still essentially nowhere. But to be more pragmatic, I think that, yes, we're getting better and better at contrail detection, especially in these geostationary satellite images. And I think it's driven by multiple things. One of them is the incredible work by Google in releasing a very large labeled data set of GOES 16 images. So GOES 16 is the geostationary satellite above the United States. And another part of it is just deep learning models becoming better, becoming larger, people coming up with smart ways to train them and think about, for example, symmetries in the problem. So we're getting better and better. Is it perfect? No. Do we have a good representation of the uncertainty of contrail detection methods? I would say that is also something that we don't really have, right? Because usually if you look at the results for contrail detection methods, so you can basically plot them on top of a satellite image, you'll see that most detection methods capture most contrails, but then some of them aren't captured. And then why does the detection method not detect a certain contrail? I think that's a question that we can still go and delve a bit deeper in, because it's very important if you think about using this data for model verification, right? It might be that the model is actually quite good, but the model is not very good at predicting the contrails that you actually observe. So it's very much recognizing that both the models and the observations are imperfect. And then, as I said earlier, really tackling those uncertainties head on, essentially.
Mm-hmm.
So that's a very long answer to a pretty simple question, I guess. I could have also given you some numbers about how many contrails we capture and how many we don't. But I think this is perhaps a bit more interesting to think about. Okay, what can we do to improve things?
I think sometimes the simple questions are the most interesting ones. A follow-up question to what you just explained. So
yeah,
there is this issue of a resolution limitation for the satellites.
Yes.
And to break this down, for me, an analogy would be if I'm standing in the desert and, in a far distance, someone's approaching me, then there is like one point or one distance after which I will recognize that someone is approaching me, And this is with regards to my resolution of my eyes, let's say, right? And the satellites, they also have a certain resolution. And the issue with that is that right now we have a blind spot. Initially, when the contrail forms, way before it then converts into a persistent contrail or a cirrus cloud, right? There is this like blind spot because we can't yet see it. It's like too small. Maybe you could elaborate on that problem. Is it more a problem that hinders us in actually detecting and allocating contrails, or is it more a problem for model verification and understanding what is happening, initially in the formation phase?
So I quite like that analogy you just came up with. So indeed, for example, the resolution of the GO-16 satellite is about 2 kilometers, and then it gets progressively worse as you look further up or down on the Earth, so like higher latitudes, lower latitudes. And so it doesn't really affect our ability to detect contrails if you compare it to human labels, right? Because the human labels also, humans can only see a contrail at a certain point, right? And it doesn't really affect the results of a detection method. It does affect the contrails you can see, but not necessarily, okay, how well can the detection method do? But your previous question, I realized, had a second sort of component that I didn't talk about the ability to take a contrail detected in a satellite image and then relate it back to the flight that actually formed it. And that's really where this sort of blind spot or appearance lag, essentially, this time it takes for a contrail when it forms to grow sufficiently large and optically thick to become visible on a satellite image. That really hurts you there, because one of the main problems if you're looking at, okay, which flight created which contrail, is that one thing you can do is you can look at the flight data and then basically do this sort of thought experiment or a computational experiment where you say, okay, the flight was here, what does the wind data say, where, if it had formed a contrail, would that contrail show up in the satellite image? And because of the time it takes, this appearance lag, which is, well, let's say it varies around half an hour or so. I'm not exactly sure about that. And it also depends, obviously, on the instrument that you're using. The wind data, although it is really quite good, the wind data from numerical weather prediction models, especially when you compare it, for example, to their estimates of humidity in the upper troposphere, very small uncertainties can lead to quite a large discrepancy. If you have a uncertainty of 3 meters per second in your wind, so like a typical error of 3 meters per second, 2 meters per second, and it takes half an hour, then the discrepancy can be about 5 kilometers, right? So you're going to locate the contrail at a distance, at a position that is within 5 kilometers either side of its actual location. And that might not seem a lot, but 5 kilometers is already 2-3 pixels, and in areas of very high traffic density, like in the US, in Europe, that can really hamper your ability to unambiguously say this flight from this contrail. So I think that's really where it comes into play a lot. And obviously also for contrail models, you cannot really observe the first couple of phases of the contrail evolution, right? So the jet phase, that is right after the engine exhaust starts mixing with the ambient air, and the vortex phase where it interacts with the wingtip vortices. You do not really observe those parts of the contrail lifetime when you use a geostationary satellite. So it's very important to keep that in mind if you're using these observations for validating a contrail model. It will mostly be about the adolescence of the contrail, so to say.
And this touches also on the propagation of uncertainties, right? Taking into account that there are many steps, but each step has inherent uncertainties.
Mm-hmm.
And so the accumulation of these uncertainties has to be taken into account when making definite decisions at the end of the pipeline, right? So that is also part of your research, isn't it?
It's not explicitly something I've published on, but I do try to prioritize this for any future research. I think there's also other interesting research going on by other groups like Google and Breakthrough Energy, that they are using a certain physical model of contrail evolution and then trying to see, okay, what is the effect of uncertainty in the weather data? And it is essentially a very complicated bookkeeping problem where you need to assess properly what are the uncertainties in the input, right? So there could be the wind data, the humidity data, then what is the uncertainty in the model? I think that is, in my opinion, the hardest one, right? Because essentially what you'd like to say is, if I use this particular model, as I said before, you get an output and I should take that output to be a uncertainty distribution. That is something that I think really hasn't been quantified that much so far. So yes, I duly hope there is going to be more research published soon about taking into account all of these uncertainties and seeing what is the effect on the final estimate, right? Because it's not only the model that might be slightly off, it's also very much the weather data that can be off. And that also makes it hard to quantify how wrong is the model, because it's essentially, if you come back to the old adage where you say garbage in, garbage out, right? So that makes model verification in itself also quite a tricky endeavor.
And garbage out is the key word for a point I wanted to mention as well. And that is whenever you make binary predictions, let's say there is an ISSR or there's not an ISSR, then you can, for each of these predictions, you can be right, when you evaluate it afterwards, or you can be wrong. And this is called the contingency matrix.
Yeah.
I'm wondering, what are the pitfalls in this contrail prediction? Can we, even taking into account the two options where we do false predictions and act upon it, still have a net positive effect to make aviation more sustainable?
So yeah, let me just quickly reiterate about this contingency table, right? So it's like it's not really something we should describe on a podcast, to be honest, but it's a 2x2 table, right? And essentially there's two types of correct answers when you do a prediction about whether a contrail is going to form and persist. There's a true positive, which means that you predicted correctly a contrail formed and persisted, and there's a true negative where you predicted correctly that there wasn't going to be one. And he also has two types of errors: a false negative, which basically means a contrail did form and persist and you didn't predict it, and a false positive where you said a contrail was going to form and persist, but actually you don't observe one. And the thing is, if you think about contrail management, it's actually, you need another contingency table, which is becomes a 4x4 table, because it's all about being correct twice in a row, right? You're flying at a certain altitude, or let's assume that the contrail avoidance tactical strategy we're using is just making vertical deviations. Then you need to be correct on the original altitude and the altitude that you're going to deviate your aircraft to. And this is one of the things that I investigated as part of my research during my PhD. And essentially what we saw is that we accounted for the possibility of making mistakes, right? And when you make a mistake, certain mistakes are worse than others. For example, if you're flying and you make a prediction about you're going to form a contrail, and then you're going to deviate into a region, obviously, where you predict you're not going to form a contrail. If it turns out that the region you intended to avoid never actually occurred, so that's a false positive, and you deviate into a region that you predicted wouldn't be there, so that's a false negative, that's probably the worst kind of error, if you assume that contrails are warming, right? Because of the deviation, you might have burned a bit of extra fuel, and perhaps other kind of costs like extra flying time. You have formed an additional contrail due to the deviation. That's probably the worst kind of error. But even if you can account for these things, and it depends on the assumed ratio of the warming impact of a typical contrail to the warming impact of additional fuel burn. But it seems likely, in my opinion, even for assuming very conservative values of that ratio, that even with existing forecast products, we can actually do contrail avoidance. But the benefits are going to be quite a bit lower than previous estimates in the literature.
Okay, so you're talking about the literature here right now, and because there are also already players who are implementing this, right? Mm-hmm. And they are essentially using the literature as the blueprint, right? And for the whole calculation of the net benefit. And what you're saying is that so there is a little bit of bad news, but mostly good news, I'd say. So the good news is that, yes, even if we differentiate and add one layer of complexity to it, and that is also, okay, what happens if you deviate? Let's look into that area too. If you take that into account too, then still it is overall something that has a net benefit for us. However, if we do take it into account, then we've been overestimating the benefit of that deviation beforehand.
Yeah, and it also depends on what estimate you're looking at from the literature, right? If you look at an estimate that actually accounts for these errors, that it will be much more in line with the results that I found. And I think this is just one example of doing a study where you say, okay, we're going to look at the worst case scenarios and then actually finding that things aren't as bad. They're definitely not as good as we assume, but they're not as bad as they could be, right? So I think that's one kind of sort of approach to research that I'd like to continue. Basically, beforehand, think of all the ways something can go wrong, put a best possible estimate of the probability and the risk, essentially, of that worst case scenario occurring, and then figuring out, in the end, do we still come down the line, do we still have a benefit or not? And it seems like we do. Again, I must emphasize, it really depends on the ratio between the warming impact of contrails and the extra fuel burn you use. But even for conservative estimates, like a factor of 10 difference, which I think seems conservative, you would still be able to attain benefits.
You're referring to the topic of the equivalencies here, right? How do you calculate the equivalency between the fuel penalty, let's say, and the warming effect of a persistent contrail?
Yeah, exactly. And that is something that I did not very much specify in my research, because you can imagine there's a lot of ongoing research about how should we calculate that, right? Mm-hmm. Obviously, you can get estimates of radiative forcing or the energy forcing of a contrail, and then also the impact of fuel burn. But then you also have questions about, okay, which kind of climate metric do you express it? So there's a whole lot of questions out there. And I think what I really tried to do in that part of my research was basically compartmentalize it and say, okay, this ratio between the impact of a contrail and the extra impact due to burning fuel, that is something that's going to be specified later. And I think within the framework, you're free to do that.
Mm-hmm. Inherently, or essentially, these two effects that you have. So you're directly emitting CO2 versus you're creating clouds which act like a mirror, right? Mm-hmm. In super simple terms. They are very hard to compare, but there is a way to compare this through metrics. And you can then decide, okay, so over what kind of a time frame do you want to compare these two things? And this is a really fundamental decision and really influences the outcome of which effect overweighs, right? And in my opinion, this is a political decision. This is something, one generation has to decide how much they care about the next generation. But what you're saying, and I find this so interesting, this is why I'm stressing this, is that even if you take the conservative approach, right? Yeah. And a conservative approach would mean that you look at a longer time frame, because the CO2, remains in the atmosphere for longer, has a long-term effect. Even if you look at that end of the spectrum, then still taking into account the more sophisticated, let's say 4x4 matrix you said earlier, right? But essentially a more differentiated approach, it still seems to be a positive impact overall.
Yes. I didn't do that calculation specifically. I just came up with a number that look reasonable, but that is one way to arrive at such conservative values, right? Like taking a really long time horizon, for example. And even then, I think that one of the things that you can also use from that research we did is basically say, okay, well, we know for sure that this is the ratio. It's probably never going to happen, but we're for sure that this is the ratio. How good should our forecast be so that we get benefits from doing contour avoidance, given that this is the ratio? Right, you can also determine that. Mm-hmm. So I think we just need a slightly different framework for assessing forecasts of contour formation and persistence when you're looking specifically at contour avoidance.
Right. So we've spoken a lot about the pipeline and about uncertainties. Now, something that has been discussed more and more recently is the inclusion of ground cameras. There has been research around the inclusion for a long time already, but there seems to be more of a development or maybe larger networks of cameras that we could tap into. And what role do these ground cameras actually play in improving contrail prediction?
Yeah, as we talked about before, right? So there's this time period. You called it the blind spot. I call it appearance lag. I also had this discussion about what to call it with Steven at some point. Anyways, there's a time between contrail formation and the time you can first observe it using a geostationary satellite, right? And one of the ideas of using ground-based cameras is that you can see a contrail right when it forms, under specific circumstances, meaning that it's not there's not a large cloud cover below the contrail, and it's during the day, and that might even not be necessary given some of these cameras that also are used to study meteors, right? So that is, I think, where it mostly will come into play. I think one of the exciting ideas that I have, but I think also other people have, and it's quite a open door, so to say, is to use a ground-based camera to ascertain, okay, which contrail was formed by which flight, and then try to figure out, try to track those contrails you see on the ground-based camera up until they become observable in a satellite image. And then you have a data set, sort of a ground truth, which says, okay, these contrails that I now see on my satellite image, I know which flight formed them. And then you can take an existing algorithm that is doing this matching, for example, like the one that Google published about, and then you can start scoring it. And you can take those scores, for example, it might be correct 75% of the time, and you can take that 75% as a score to start doing things with it in downstream applications, right? You might not want to, if it ever comes to a position where you would use satellite images to say, this flight formed a contrail and this one didn't, and you would use that to allocate some kind of penalty or incentive, and then that 75% becomes very important, right? Because you might not want to give the 100% of the tax or the incentive to a particular flight then, because you're not entirely sure about things. So it all comes back to this idea that if you have a pipeline, characterize the uncertainties and try to figure out how does a downstream component, how is that affected by the uncertainties in an upstream component.
Okay, so it can play a role in increasing our certainty and be like an indirect help as well in, doing the contrail prediction.
Yeah.
Another question I have, and you might notice that I'm slipping in some of the counter arguments here and there, and you as an expert help us to understand how strong or weak, these arguments are. And I think you've already done a great job with the earlier arguments. And another argument that I hear sometimes is this question of the water budget. So one flight an aircraft goes through an ISSR, and what happens to the next aircraft that goes, shortly afterwards, that goes through the same kind of an area? Was there some kind of water budget before that is now consumed? And what is the relationship, between the two potential contrails that can form for these two flights? So where do we stand with regards to knowledge and certainty in this tough question?
Yeah, I think that is basically the way in which contrail formation and persistence affects the water budget, and then the effect that has on other flights flying through and forming a contrail, and the climate impact of that particular contrail. That is something that we need to tackle. I think the way we're currently looking at our prediction capabilities for contrails, especially in the role of contrail avoidance, is very much the first order thing we're looking at is, okay, can we actually predict whether a contrail persists? And perhaps also what is the energy forcing of that contrail. But really the second order effects are that water budget question, and also the question about, okay, if we don't form a contrail, or if we do form a contrail, how does that affect the, how would you say that, essentially the amount of aerosols, right? Because the aircraft engines also emit aerosols. How does that affect other cloud formation, right? But the first thing is the water budget. So I think with the water budget, one of the main studies I can think of is the one by Professor Schumann from 2015, where he basically implemented COSIP, which is one of those contrail formation and evolution models, in a larger global circulation model, and then looked at, okay, what is the effect? And he definitely did find an effect, right? The contrails that formed after contrails already formed in a particular region will become thinner and also longer lived. I'm not actually sure about what the individual impact was between like the first comers and then the late comers essentially. But there is definitely an effect. And I think there's also one thing that we found in observational studies, which is not necessarily due to the water budget, but what we found in the study that I did from 2022, and then Google also found it in a follow-up study, is that if you look at the diurnal pattern in flights over the US and the diurnal pattern in contrail coverage, you see that the contrail coverage pretty much peaks right after the early morning peak in flight traffic. And then the flight traffic more or less remains constant throughout the day. But actually the contrail coverage decreases a bit. At least that's what you find when you use these models for detecting them. And that it could very well be an observational effect where, for example, the contrails that formed earlier in the day, they spread out, form a layer of background cirrus that makes it harder to actually observe the contrails that form after. But it could also be a water budget effect, right? So that is, I think, an open question that deserves a bit more attention as well. And I think it also would make sense to repeat the study by Professor Schumann using a different, perhaps climate model. I think it's something that's being overlooked a bit. And I think it's also something that might be very interesting to tackle with actual experiments. So with actual flights flying through a particular region and other flights with adequate measurement equipment.
I also hope that there will be more trials. And with the European Commission putting out this innovation fund, where actually there were some applications, and then hopefully in September we get positive results that the consortia, which have airlines in them and who want to do practical trials, that they get this fund or subsidy. It's not entirely subsidized, but at least get the support to do this. This will certainly be an important step. And I was smiling when you answered, because when Roger Teo was on episode 11, and when I asked him the very same question about the water budget, he also pointed to the 2015 study of Professor Schumann. So this is another official invitation for Professor Schumann to join the show as well and discuss this important topic, and maybe also, prepare the stage for follow-up studies. And you said that, it would be interesting to do such a follow-up study also with other models. And right now, I see that there is a pretty heavy focus on the COSIP model for this prediction. And I'm asking myself, is this a bias in itself already, or is it fair to do most studies based on the COSIP model versus ACCFs or other models?
I think scientifically speaking, if you look at the typical approaches taken, for example, in coming up with estimates for the IPCC reports, then it's not a good idea to only use one model. However, I do understand why many researchers pick COSIP, right? It is relatively fast. You can understand the model quite well because it's not very complicated, both from a numerical as well as a physical perspective. Well, physical maybe a bit more because there's quite a lot of processes going on. And it's also open source now, right? From the excellent work by Breakthrough Energy, amongst others. So I understand that it's being used a lot, but I think it will be interesting also to use other models like ABCAM, which was developed at MIT, a bit more. I think there's also other research going on into making other simplified models for contrail formation evolution, but I can't say too much about that. It's definitely not ideal to have only one model which is used so much. It also speaks to a lot of good work done by Professor Schumann and also Breakthrough, right, in open sourcing. So I understand it. I don't think it's necessarily the best approach, but it is understandable. But I also know that Breakthrough Energy, for example, is very keen on using that Python package they have by Contrails, and then exposing other kinds of models like ABCAM through that Python interface. And I think they've recently finished that for ABCAM. So it's definitely on their agenda as well, I think.
A very nuanced answer to another challenging question here. And now we've spoken about so many different aspects, and I'm trying to wrap up this super interesting episode here with you. And we've touched upon many topics, but maybe not every topic is equally important, also in informing us for a next action that we should take. So, closing the circle, and with regards to the MRV and the maturity of our contrail prediction pipeline, the observation maturity, etc., are we ready to have a system that supports the MRV or any other system?
That's hard to answer, because I think there's a thing that we should do. If you look at the observations that are mostly used to look at, for example, how good GOSIP is, and there's this other good study by Schumann and others from 2017, where they basically compare almost all observations done on contrails, both through in situ and remote sensing. With GOSIP, you see that they agree more or less, but these are all observations from different contrails at different lifetimes, right? But GOSIP is a model, for example, and I'm looking at GOSIP mostly, but I think many of these models would essentially quantify the impact of a particular contrail over its lifetime, right? And we don't really have that much data of the properties of individual contrails over their lifetime. And that is ultimately what you're going to predict. So that's something I'd like to see, right? It might start with optical depth as a function of lifetime. And then based on the error that a particular model makes, I think you can probably figure out, okay, what's the error in the energy forcing? And if you do that, it might turn out that we're perfectly capable of doing this already. And then you might as well put your foot on the gas when it comes to the EU MRV system. But I think that's really something that is essential to do. And I think also with contrails is probably one of the easier non-CO2 climate impact pathways of aviation, with which we can do this, right? Because if you start thinking about, okay, how can we use observations to, for example, quantify how good are we at modeling the impact of NOx emitted by aviation on ozone, that is going to be far more complicated. I think with contrails it might be a bit simpler. So I think that is really one thing I would like to see. Really measurement campaigns, or also remote sensing studies that really look at individual contrails and then compare them to the predictions of different models. And then come up with that ultimate error estimate where we can essentially say, okay, how good are we? Where do we need to invest more resources in it when it comes to prediction?
Okay, and I mean, data is the complete basis of your work, and every decision should be a data-driven decision as well. So when it comes to the data being collected, you as a researcher, is there any scope or any requirement that you have for the data that is being collected? For example, any particular flight that is more useful than, for example, short haul or long haul flight? Any data that is more or less useful to be collected? Or would you say we should collect as much data as possible?
I think beggars can't be choosers in this question, right? So I would already be very happy with any kind of data set that does that. And obviously, I will try as part of my research to help as much as possible in collecting data sets like that. I probably, when I think about it more deeply, I'll figure out, okay, we might want to really focus on this particular flight in this particular region. That might tell us more, but I don't really have a really suitable answer to that. I feel like in general, if you look at all the satellites we have flying around, well, they're not flying around, but orbiting our Earth, there's a lot of things we can still do by, for example, collocating different satellite instruments, ground-based cameras. So I think we just need more and more people doing very challenging work and really trying to find that needle in the haystack when it comes to these large sets of data.
Brilliant. In the tradition of this podcast, I've already slipped in a question from the previous guest, and the next guest will be Professor Paul Williams. And we'll explore a little bit the aspect of what is actually the environment doing to aviation. So the other way around, and not just what is aviation doing to the environment. Is there a question that comes to mind that I should ask?
So I'm very much interested in hearing about what he thinks about the essentially the correlation between clear air turbulence, or the presence of clear air turbulence, or any kind of turbulence, and ice supersaturated regions. With the idea that if we avoid ice supersaturated regions, would that increase or decrease passenger comfort, for example?
I'm both excited and afraid of the answer.
Yeah.
That is a brilliant question. I'll take it on. And another question I have to you is, if you could wish for one guest that I should interview here on the podcast that has not yet been on the show, who would come to mind?
I think there's many. I think Professor Schumann would be interesting. I think Klaus Gierens would be interesting. There's probably other names that I cannot think of right now. I think you could probably hit the 50 episode mark, and there's still some interesting people that you haven't interviewed by that time. So yeah, and even if you don't, like sometimes a new episode pops up, and then I see a name that I didn't really know, and then I listen to it, and I'm like, oh wow, this is very interesting. I've learned something new, and then start looking more into what this person is doing. So it's always also good to invite people that I might not think of, essentially.
Great. Yeah, you're right. It's all about that mix.
Mm-hmm.
Now, since we have so many curious people in our audience, is there any resource that you would recommend for anyone who's interested in learning more about your research that I could link in the show notes?
I think it's a bit of a large pill to swallow, but if you look at my PhD thesis, that's probably the best place to look at the research I've done so far. There's some nice, I think there's some nice diagrams in there that visualize things as well, including that blind spot or appearance lag that we talked about earlier. So hopefully people find that decently useful.
I can only support that, and you're being very modest here. I definitely support looking into that. All right, Vincent, thank you so much for being my guest today and for this brilliant interview.
Yeah, thanks a lot for having me.
Speak soon. Bye-bye.
Bye-bye.